No. Okay.
Good morning, ma'am.
Good morning. How are you?
Fine, ma'am. Ma'am, how are you?
I'm fine, thank you. Okay. Okay. Hello, Halima. Halima is connecting. Okay, hello, Nimra.
Assalamualaikum, ma'am.
How are you?
I'm good, ma'am. How are you?
Fine, thank you. Hello, Nashra.
Hello, miss.
How are you?
I'm good, miss. How are you?
I'm fine, thank you. Okay. Hello, Sahib.
Hello, ma'am.
How are you?
I'm good. What about you?
I'm fine, thank you. Okay, so what were we studying last time? What did we study last time?
Where we studied that Einstein's formula. Then we also studied fission and fusion reaction
Okay.
and the likes of it.
And the likes of it. Okay, right. So we have been talking about, we are actually practicing chapter number 5, right? So and which is about the cosmos, the universe, astronomy, the stars, the sun, and so on, and the related concepts of physics and the related applications. So the concepts we have been talking about in the last class are the important equation but powerful equation where you can convert mass to energy. And this has applications in fission and in fusion, which are huge sources of power. So we solved the problems related to this, right? And we showed how the mass difference, which is also called the mass defect, is converted into energy by using the binding energy concept, right? So this was what we were doing last time. Again, these are types of nuclear reactions. So we have already been studying this, and last time we solved problems related to this. ठीक है?
Yes, ma'am.
Okay, good. So let me take the attendance. Right. So Ahmad Hassan, Fahad bin Ahmer, Hafiza Aisha, Ali Musa, Mahnoor Amjad, Nimra Arif, Sayyid Azad Asad,
Present, ma'am.
Farooq Ahmed, Muhammad Awais Khawar Gill, Laiba Khalid, Sahib Khan, Elia
Present.
Shafqat,
Present, ma'am.
Amna Maham, Nashra Rashid, Aruba,
Present, ma'am.
okay, Aruba Riaz, Harima Ijaz, Nawab Siddiq, Sumavi Tahir, and Saul Rafaqat. Okay. So now let's go to the book. I'm going to share the book with you. So again, as I said in the beginning, you take printouts or photocopies to study so that you can make notes and you can, of course, work out the problems and so on. So it's helpful if you print them out or you photocopy them. And in addition to that, you use your notebook and your calculator and study and practice as is required. Okay. So I'm going to now share this textbook.
Miss,
Yes.
Halima Jas is waiting. Please enter her.
Actually, I have entered her.
Oh.
She connects and then she disconnects. She's having some problem. Okay, so now you can see the book, right?
Yes, ma'am.
Okay, so we were talking about stars, right? And the concepts related to stars. So in order to understand these, we have to understand the physics of how temperature is related to the wavelength emitted by a radiation, right? So this is a relationship between temperature of a body and wavelength of radiation. So temperature we know is related to heat energy. And then we also know this electromagnetic spectrum and how energy is related to wavelength. And this was something you studied in chapter number 2, right? Okay, and then we also know that temperature is related to color. And as we said that the stars, there is a fusion going on in the stars and therefore they have a high temperature and they have different stars have different temperatures, and this temperature is related to color, and this then leads to the classification and the naming of stars is done on this basis. Then another important diagram that we use in order to understand this and understand the classification is the HR diagram, the Hertzsprung-Russell diagram, which is a graph of the star's luminosity against its color or surface temperature. So we also talked about what is luminosity and what is intensity and how these are related. I showed you small formulas. Again, this is a part of this chapter. We've already studied this. And then to identify energy sources, a characteristic of each star group. And for example, we have the star groups, main sequence, red giants, and white dwarfs. Okay, so when you read carefully through the text, you will find the explanations of these concepts. So please, again, I've also uploaded videos related to this. I've uploaded the video last time related to the classification of stars on the basis of temperature and color. And then it also explains these groups of stars, the main sequence, the red giants, and the dwarfs. Now, I'm just going to go back a few pages to remind you of what I just said. You know, I talked about, you know, the formula that I showed you last time. No, not this one. The formula. Okay, it will come again after a few pages. I'll show you again. We can see it again, but of course you have the book and you can see it as many times as you like. So let's go further with this. We also talked about what is a star actually, how we define a star. Okay, right. And we know that a star is a luminous body of plasma. We talked about plasma, what is plasma, and we explained it last time. I've also written the definition here. Now, what are the various characteristics, properties of the star, the observations, the measurements that are done in order to understand them, and then to explain them, and then to classify them. So we talked about these, for example, the temperature, the pressure, the power, which is related to the luminosity, and the composition. We talked about the elements in a star, the mass, the position, and the age, and so on, right? We now we come to we continue the same topic, and this topic is also related. We are talking about radiation, we are talking about wavelength, and we are talking about how it's related to temperature. So you will see the word spectrum here several times. So what is a spectrum? I've already discussed this while we were studying chapter number 2, and I also showed you a diagram, but again, I've written a definition for you over here. The spectrum is a band of colors as seen in a rainbow, for example. So that's the electromagnetic spectrum. It's the visible part of the electromagnetic spectrum. The spectrum that's coming from the sun consists of various wavelengths, and of course, these wavelengths are related to wavelength is related to frequency, and it's related to energy, and also it's related to color. The visible part of the spectrum, we see the colors that, for example, we can see in a rainbow. We cannot see all the radiations, we can only see the visible part of the radiation. The human eye is only sensitive to that. So, but then we have some instruments and methods by which we can detect the other parts of the spectrum as well, and we can measure them, and we can perform experiments and so on. So I've written this definition here just to remind you, and I can also share a diagram to show you the spectrum. So I'm going to share the electromagnetic spectrum with you again. I shared it when we were studying chapter number 2 as well. And here you can see this diagram, right? This is the electromagnetic spectrum. This is a spectrum that comes from the sun. And you know that the sun is the biggest source of energy on Earth, right? It's producing a lot of energy, like we discussed last time, through fusion. And the sun is a star. It's a kind of a star. Now you can see that these radiations, the electromagnetic radiations, they have a wavelength ranging from very small, which is like 10⁻⁵ nanometers, and then they gradually increase and they go towards longer wavelengths. This is 1,000 meters. Okay, so nano you means you understand is 10⁻⁹. Okay, so that's very short. So we start from a short wavelength towards long wavelength, and you can see the corresponding drawing of the wave. You know, we have discussed in chapter 2 how you define the wavelength, and you know how you define the frequency and how they're interrelated. And you can also see that as we go from short wavelength towards long wavelength, the energy also changes. So long wavelength corresponds to lower energy, and short wavelength corresponds to higher energy. So, and we are then later on going to relate them to color and temperature as well. Okay, so a long wavelength is in meters, and short wavelength goes towards nanometers. And on the basis of these properties, we have divided them and given them names. For example, long wavelength radio waves are an example of long wavelengths. And then you have microwaves, infrared, and then you have this small part of the spectrum, which is from a range of, let's say, certain about hundreds of nanometers here, and then it decreases towards here. You can find the exact values from this graph. Here the frequencies are mentioned, and you can see that the longer red color corresponds to a longer wavelength, and then the remaining colors, the wavelength is decreasing, and blue color is a shorter wavelength. Okay, so, and this is the part, only this small part of the spectrum we can see it with our eyes. Okay, so these are the colors that we see. And when, you know, very simple thing you can do as a student, even as a child, is the the use of a prism, to understand this spectrum. If you just take a prism, which is a glass, and you focus it on a source of light, it can be a candle or small bulb or anything. And in order to see this clearly, you can recreate a rainbow yourself inside a room. For example, you switch off the light, you make it a dark room, you switch on a small source of light, maybe a torch or a small bulb or a small candle, and you adjust your prism in such a way that you hold a sheet of paper or maybe a white wall or anything as a background, and you will see that you will reach a position where you will see that this white light that you see from the source will be split into the wavelengths that we are looking at here: red to blue, red, orange, yellow, green, and then blue. You will see that you will observe these colors on the paper. So you recreate a rainbow. And this is the same principle by which you see the natural rainbow that sometimes appears on the sky, right? So in that case also, when the conditions are fulfilled, the droplets, for example, of rain that are hanging in the atmosphere, they sometimes, act as a prism and they split light into these wavelengths. So that's a very nice and simple thing to observe. But then this is also related to the refractive index that we studied again in chapter number 2. Okay, and then this is the visible part of the light. After that, you have the ultraviolet part. Again, you cannot see the ultraviolet part, but you must have heard of it because normally we use sunscreens, for example, to avoid the ultraviolet radiations reaching our skin because they're harmful for the skin, right? Then after that, you have X-rays. Again, X-rays are a part of the electromagnetic spectrum, but these are high energy radiations, and therefore we use them for certain, for example, in medical, for example, X-rays are used for diagnostics and so on, but you have to protect yourself and there are certain precautions that have to be taken, right? And then you're familiar with gamma rays. Gamma rays have the shortest wavelength in this spectrum and they have the highest energy. So radio waves, you use them in communication. You're familiar with microwaves are also used in several applications. And then you have this visible light and then X-rays and gamma rays, okay? So this was to remind you of what we mean by spectrum and the electromagnetic spectrum and how wavelength and energy are related, okay? So, and also you might remember in one of the last classes in this chapter as well, we talked about red shift and blue shift. So you can also understand that. We explained the Doppler's effect and how the frequency or the wavelength changes and towards longer wavelengths or shorter wavelengths. And this can help you determine whether a star is traveling towards us or away from us. Okay, so these concepts are related to those. Now I'm going to come back to the chapter. So I'm going to share the chapter again. Okay, so I have explained in detail about the spectrum, and now I will also explain the term spectroscopy, because you will, again, when you're reading this, you will see the word spectroscopy. So spectroscopy is again a word that has been derived from the spectrum, and spectroscopy is a method of study of the interaction between matter and electromagnetic radiation as a function of wavelength or frequency of the radiation, right? So in simpler words, spectroscopy is the study of color as generalized from visible light to all bands of the electromagnetic spectrum, because you need to clarify these concepts so that you can understand how the star's temperature is related to color and how you can perform spectroscopy to understand some of these concepts and then use them further. So for example, wavelength dependence of absorption by gas phase of visible light is dispersed by a prism. So we have just talked about that. Matter waves and acoustic waves can also be considered forms of radiation energy. And recently gravitational waves have been, okay, gravitational waves is very interesting, but I'm not going to go into the detail. If you're interested, you can see this, the Nobel Prize that was given for gravitational waves just recently, I think in 2017. And you might remember that there was a Pakistani origin scientist, Nargis Mevlala, who was also a part of the team who worked on this experiment. You can go and check this out. There are many videos, and again, you can find them at a very simple level where you don't need too much knowledge of physics. Again, this is not from the examination point of view, it's just from your curiosity point of view. Nargis Mevlala was the head of the physics department at MIT, and I think now she's the dean. She was also invited to Lahore, where she gave a lecture at ITU, the Information Technology University, and she was also given an award by the government of Pakistan, right? So that's also interesting. You can go and check it out. And the name of the experiment for which they were given this Nobel Prize is called LIGO or LIGO, however you like to pronounce it. Okay, so this was just a side note, just for your interest and curiosity. Now, just as I said that intensity, for example, I also talked about this last time. So intensity is a term that you will be again using while you're talking about this topic of the energy of the stars and the temperature and the color. And intensity, as we saw the formulas last time as well, the intensity is the power received over each square meter, and its units are watts per meter squared. So intensity, and the symbol used is capital I. So you can see the formula here. So intensity is written like this. So again, this power that is received or emitted is measured, and then this can be related to the luminosity of the star. Okay, so this is the definition here and an explanation. And here you can see different stars have different luminosity, and they have different temperature, and they have different brightness, right? So there's another term which is called luminosity, and luminosity is the total power output from a body, right? And in this case, we're talking about stars, okay? So you can see that, again, if you want to calculate the luminosity of a body, which in this case is a star, you will need the distance, for example, and the intensity, and then you can calculate it. And a formula that can be used is given over here. In this case, capital L is the luminosity, which is output power, and hence its units are watts. And this power will be spread across the surface of a sphere with a radius equal to the star's distance. So in this case, this is the distance, and this is the luminosity, and intensity, we've just defined it before, and then you can relate them and you can calculate the luminosity. Okay, so this is a small formula that you can use. Now, coming to color and temperature. When we talk about color and temperature, we are talking about black body radiation. Okay, so black body radiation is the concept that relates intensity and wavelength, and this is related to temperature. Again, a very simple observation from everyday life, is that when we heat something, you will see that the color changes. Okay. And a very simple example is, for example, if we have a piece of iron and we heat it, you will see that it becomes red. So you see the temperature is related to color. And then as the temperature changes, then it might change from red to yellow. And then it becomes, after a certain temperature, it becomes white. So you see, as the temperature is changing, the color is also changing. Okay. So stars behave in the same way, and their colors depend on temperatures at their surface. And here we have an example of a star. Antares is a star which has a temperature of about 3400 K. What is K? What is K? Yes. What is K? G, who will answer this? I'll give you a point for this. Yes, come on. What is K? सो गए हो?
No, ma'am.
Yes, what is K? कौन बोला था अभी?
Elia, ma'am.
एलिया बताओ, what is K?
Ma'am. K.
K is the unit for,
Kinetic energy.
no, in this case we are not talking, okay, kinetic energy.
Kelvin, ma'am.
Kelvin, yes. कौन बोला?
Saul Rafaqat.
Very good. So can you tell us Kelvin क्या होता है? It's the unit of? Kelvin is the unit of?
Ma'am, ये heat,
Heat नहीं बल्कि temperature.
energy, sorry, temperature, ma'am.
Unit of temperature.
Temperature.
So what is the unit of temperature you're familiar with? Which unit of temperature do you use in your everyday life?
Degree Celsius.
Celsius, okay, you use Celsius, okay. So Celsius, the symbol for Celsius is C. The SI unit for temperature is what? The SI unit for temperature is? This is from chapter 1 actually, you know, we studied units in chapter 1. Yes. The SI unit for temperature is Kelvin. Okay. So
Kelvin.
scientifically, when we talk about temperature, when we do calculations about temperature, we do it in Kelvin. But in everyday life, we use Celsius. We also sometimes use Fahrenheit. You might, you know, for example, when you're checking the weather, you know, what's the temperature today in Lahore? So you have to also write the unit. So normally we're not using Kelvin in that case. But when we're talking about scientific studies, we're using the SI unit, which is Kelvin. And how do you convert Celsius to Kelvin? 1 Celsius is equal to 273 Kelvin, right? Okay. So again, we have talked about a black body, the concept of a black body in physics. So black body is an idealized concept of an opaque, non-reflective body. You know that whenever heat or radiation falls on a body, a part of it is absorbed and a part of it is reflected. But we are talking about a body, a black body is a idealized concept of a body in which we assume that there is perfect absorption and no reflection. Okay, so in this case the radiation from a black body is a thermal electromagnetic radiation, so which is heat radiation within or surrounding a body in thermodynamic equilibrium with its environment, and this is emitted by a black body. It has a specific spectrum of wavelengths which are inversely related to intensity that depend only on the body's temperature. So you see that wavelength is inversely proportional to energy, as you just saw in the diagram also that I showed you, right? So we saw that longer wavelength was corresponding to lower energy and higher wavelength was corresponding to so shorter wavelength was corresponding to higher energy. So here you can see the black body graph, right? You can see the wavelength here in nanometers and you can see the intensity here. And you can see how the wavelength changes with intensity, okay? So as the wavelength is becoming longer, this intensity is decreasing, right, in this case. And this is the formula for this, the power or the luminosity, you know, we just saw this is L, okay, this is equal to sigma A into T raised to 4. Sigma is a constant, which is known as the Boltzmann constant. A is the surface area of the body and T is the absolute temperature. And again, you will notice that here the temperature, for example, is in kelvins, in K. And you can see as the temperature of the body is changing, the graph is also changing, okay? So you can again study this from here, right? So a black body, for example, with 6000 K will have a spectrum that peaks at this wavelength, right? And since stars behave as black bodies, okay, we find that the hotter the star, the bluer its color. So the color of the star will change according to its temperature. And the cooler the star, the redder will be its color. So if it's getting cool, the color goes towards red. If it's getting hotter, it goes towards blue. And the luminosity and absolute magnitude of a star depend on the luminosity depends upon the surface area, like we just saw. It depends on A from this formula, and it depends on the fourth power of the temperature. And so therefore changing the temperature changes the luminosity. Okay, so a small change in temperature means a large change in luminosity. So using these concepts, we can classify stars. Okay, so stars can be classified on the basis of these concepts. On the basis of the temperature and the luminosity, and according to this, they have been classified. Now I'm going to share a video in which this has been explained very nicely and simply, and I've also uploaded the link for this video, and you can also see that. So I'm going to now share the video with you. Where is the video? This one. Okay, can you see this video?
Yes, ma'am.
Good. So this is about the classification of stars, their spectral analysis, and the HR diagram that we've just talked about. Okay. So we know that the Big Bang, we are familiar with that. We talked about that in our previous classes. And now we're going to talk about what happened after that and how we can classify the stars and relate them to temperature and so on. So
what happened next? The answer to this question will require that we learn more about stars and their characteristics, which determine the way we categorize them. When we first started to...
So for example, if the colors of the stars have been classified as, let's say, white, yellow, red, and then deep red, okay, depending upon their temperature.
Observe stars in telescopes. We can L for yellow.
So now these are some symbols that have been given for these groups of stars. So white corresponds to A to D. You will see such names when you look at different classifications of stars, and M and N and E and L and so on. So,
M and N for red. This letter system was retained because all the work we now have O, B by early astronomer Annie Jump Cannon.
so then you can see that this surface temperature this range of temperature has been divided into different groups of stars. So you can see 25,000 Kelvin corresponds to O, and then in between they've been divided into different categories, and then you have up till 3,500 K, which corresponds to M.
This sequence of letters, if you find on temperature, is types of data, which we
Now
saw
this is the graph that we just saw for a black body, and in this case you can see at different temperatures you have different wavelengths, right? And this is based on this black body radiation law that we just studied. Okay.
Modern physics series are and correlated with a particular temperature as well.
And then we see the temperature is also related to composition of the star. Composition of the star means the elements inside that star, right?
As with specific elements, nuclei that have been stripped of their electrons without an electron and thus can't absorb and emit light.
So this is about, we talked about hydrogen, we talked about plasma. So this is explaining that, okay?
Helium is still better than planets like O and B stars are blue, and cooler objects resulting from the fact that so much more fuel is being...
Okay, so color also correlates with the size of the star, and it correlates with the luminosity of the star, okay?
Presented on something called a Hertz.
And this is the diagram we were talking about, the HR diagram or the Hertzsprung-Russell diagram.
Hertzsprung-Russell diagram, or an HR diagram for short.
And here you can see how the stars have been grouped together on the basis of different characteristics. So the biggest group is known as the main sequence. Then you have the giants, and then you have the supergiants, and you have the white dwarfs. And this is Antares that we just talked about.
This diagram, the horizontal axis shows temperature.
And you can also see that along the x-axis, we have the temperature, and here.
Decreasing to the right. And the vertical axis.
And here we have the luminosity. So this is the temperature starts from a high temperature towards a low temperature. So high temperature is on this side. The stars on this side are in the color range of white and blue. And as the temperature is decreasing, they become yellow and then red. And this is the luminosity, the power emitted by the star. And the luminosity for the sun is taken as 1. Okay.
Shows luminosity increasing. That all stars follow this trend up like white dwarfs. Luminosity. We also see color clearly correlating with this data collected by looking.
So have you ever seen stars like this, like in this diagram? Have you ever looked at the sky and seen something like this?
Yes, ma'am.
Who is speaking?
Sahib.
Sahib, where did you see it?
When I went to, I mean, I'm from Balochistan, Quetta, so there is no there's no pollution there, so it is
Yes.
visible from there.
Yes, that's right. You cannot see this in Lahore because we have a lot of light pollution. But if you go out of the city, you go to an area where there's less light pollution, you will observe the sky like this, and it's beautiful. Which means you can see a lot of stars. In Lahore, you don't see most of them. Okay, you see very few.
At hundreds of thousands of stars in the early 20th century that we just described. It explains why the blue star is smaller red stars, short outward pressure to prevent collapse.
Okay, so we talked about the relationship between temperature and color, and now it's also related to size, and it's also related to pressure.
So that's some basics, or 1 to 200 times the mass of our tweet. These are 3 main classes of stars.
So these are the 3 main classes of stars that we just saw in the diagram: the main sequence, the red giant, and the white dwarf.
Most of the stars that are static, they will move between. Let's move forward and learn tutorials. Support me on how is it that stars event.
Okay, so you can see how the masses have also been given over here. You can see the blue stars, they are hot, they're bright, they're big, they're bigger in size. Okay, so they correspond to 200 solar masses. Solar masses is a unit in which the mass of a star is measured. It's not measured in kg, of course. The kg is the unit of mass in the SI system, but as we know that distance, for example, in the universe is not measured in meter, it's measured in light years, because it's very huge. So a meter becomes a very small unit. Similarly, mass in the case of these bodies, the astronomical bodies, is measured in solar masses. The sun is taken as 1 solar mass, and then all the other masses are measured in comparison to those. Okay, so the highest mass is the blue stars. They're the biggest, they're the hottest, and they're the brightest. Then you have the yellow stars, they're in between. And then the red stars are small, cool, dim, and so on. And then we have the red giants, and then we have the white dwarfs, which are tiny and hot. Okay. So again, like I told you, I have given you the link and you can watch this yourself. So I will give 1 point to Saul for answering the question.
Thank you, ma'am.
You're welcome. Okay. So
Ma'am, I also contributed.
Sahib, yes, you told me that you saw the stars. I'll ask you another question, okay? So this explanation that we saw in the video is given here in your book. I showed you the video so that it helps you understand this better, okay? Because sometimes a visual explanation helps understanding what's written in the text, right? Can you see the book? What can you see right now?
Ma'am, video paused.
Acha, no, I am actually now on the book. So share screen, and this is the book. Share. So you can see here, yeah, I was saying that what I just discussed in what was just shown in the video corresponds to what is in the book. So like I told you, to prepare for this chapter, you first read from the book, then you watch the videos, then you practice the problems, and you're good to go. Okay, so for example, we talked about these types of stars, right? They are mentioned over here. So you also saw them in the video as well. And this is the HR diagram that we just discussed. Okay, this diagram relates these colors and this luminosity here on this side, and then on the mass. Okay, so this is a plot of luminosity against color, and because color is related to temperature, as we just discussed, and we can see this represented over here, and you can see the various groups of stars, or the various classifications of stars on these bases. Okay, ठीक है?
मैम
Yes, the meeting is going to end. जल्दी से पूछो.
मैम ये क्वेश्चन पूछना था कि ये सारे इस डायग्राम को हमें मेमोराइज करने की जरूरत तो नहीं?
No, you
For
need to
exam point of view.
understand it. You don't have to memorize anything. You need to